Good afternoon, everyone, and a very warm welcome to the special webinar organized by JNTUGV. This is on the occasion of National Technology Day 2025. Today's session, titled An Introduction to Quantum Communication, aims to explore emerging trends and practical insights into the quantum communications technologies, a field of strategic, academic, and national interest. We are privileged to have with our distinguished speakers and esteemed members of our academic community. To formally begin the proceedings, I now invite our respected Registrar Madam Professor G. Jayasuma Garu to deliver the inaugural address. Madam, over to you.
Thank you, Anil.
Okay. Madam.
I wish a National Technology Day. Respected Vice Chancellor Madam and the resource person, Mukherjee Garu, and the coordinator of this event, Anil, and the participants. Very good evening to all the members. So this is on the eve of the Technology Day. The India has been successfully done a scientific capabilities, and it has been launched a nuclear test. On occasion of that, this National Technology Day has been symbolized. So this.
Madam, your mic is good. Madam. Jayasuma, Madam.
You are not able to hear it, Anil? Anil?
You went on
Madam,
mute.
yes, madam. Yes, madam. You are
Now audible.
Now audible.
Now audible? Okay.
Yes, ma'am. Yes.
Yeah. Sorry for the disturbance. Respected VC Madam and the resource person and the coordinator of today's event and the participants, warm welcome to this National Technology Day seminar on quantum communication. This is on the eve of the successful completion of nuclear test in India. This they have been remembering this and given a title as National Technology Day on May 11th. In 1998, they have performed this test. From that day, they have been introduced this National Technology Day. Technology is not only the combination of hardware and the software, but it is
Ma'am, again you are on mute.
Madam, someone is muting mic.
yeah. You just take the control.
Okay.
Take the control, then I can unmute myself. You mute all.
Okay.
Now you are able to hear me?
Yes, ma'am. Yes, ma'am.
Yeah. It is about the solving problems and improving the lives and shaping the better future. So here we are traveling from the space mission to the digital payments. All these activities have been advanced due to the technology. As a professor of information technology, I wish this lecture will contribute well to the society by introducing this quantum communication, as JNTUGV is also trying to introduce a quantum computing as a minor course by the direction of ASCT as well as the direction of Higher Education Department of Andhra Pradesh. So all the student educators, professionals and citizens must continue to encourage the innovation, nurture the curiosity, and invest in the knowledge. So I wish this seminar will help you to explore in the field of quantum computing, or introducing the quantum computers into the curriculum of engineering. So I thank for this opportunity. Thank you, sir. Anil, sir.
Thank you, madam. Thank you for your very much, ma'am, for your thoughtful and motivating address. We are now honored to invite our Honorable Vice Chancellor, Madam Professor D. Rajalakshmi Garu, to deliver the keynote remarks. Madam, we request you to kindly address the gathering. Madam, Rajalakshmi, Madam.
Madam, Rajalakshmi, madam, please unmute yourself, madam. I'll give you her a quick call.
Okay, ma'am.
Anil, madam is unable to unmute. It seems if we can you help her to unmute?
Madam, she is a presenter, madam. She can unmute.
But she is unable to do it in her mobile, it seems.
Okay, maybe the problem with mobile.
Madam,
Yeah. Am I audible now? Now it's
yes, ma'am.
unmuted.
Yes, ma'am.
Yeah.
Yes.
Thank you, Mr. Anil. Today's speaker, Mukherjee Garu, scientist E from CDAC. Our registrar of the university, Professor G. Jayasuma, coordinator of this session, Mr. Anil from DMC, participants. I welcome all to this session on quantum communications. I appreciate the university, especially registrar, for initiating this quantum communications on the eve of commemorating on the eve of National Technology Day. You know pretty well about the importance of the technology, and Honorable CM Garu more focused on this quantum computing and Quantum Valley. Also, they are going to be introduced at Amravati. So on this occasion, my appreciations to initiate and higher education, APSHA also in the curriculum, they are introducing the common curriculum. It will be taken as a minor. So it's high time for all of us to focus more on, instead of normal bits 0 and 1, is high time to move to quantum bits. So on this occasion, my hearty congratulations to DMC and especially Registrar Madam for initiating this quantum communications for the benefit of all the faculty and the students. I hope this will be very much useful to all the participants and especially students, educators and faculty members, and research also. It is progressing. It is in a progressing stage. So I wish all the researchers they will be benefited by attending the sessions like these quantum communications. Thank you very much for giving me this opportunity. Thank you.
Thank you, madam, for your inspiring words, for setting the tone for today's technical session. Now it's my pleasure to introduce today's distinguished resource person, Mr. Arka Mukherjee, sir. Arka Mukherjee, sir, works as a scientist E and a team leader at the Central for Development of Telematics, CDOT, a telecom technology center of the Government of India. and is responsible for the hardware design aspects of fiber-based quantum key distribution (QKD) systems. He has over 12 years of experience designing embedded hardware for optical access networks and QKD system. He is a gold medalist in Master Science Research from the Indian Institute of Technology, Delhi. He holds a bachelor degree in Electronics and Telecommunication Engineering from Jadavpur University, Kolkata, India. He has authored multiple technical articles in peer-reviewed international journals, technical magazines, and conferences. With that, I now hand over to session to Mr. Arka Mukherjee Garu. Sir, this platform is yours. Please.
Okay. Thank you, JNTU team, for inviting me as a resource person for this event on the occasion of National Technology Day. With permission from respected Vice Chancellor and respected Register Ma'am, I'm starting the presentation for today. So today the presentation will have basically two parts. So first thing will be the introduction to quantum communications. Then I will highlight a bit of what CDOT is doing in this field and how our solutions can be benefited for the educational setup also. So thank you, Dr. Anil, for the introductions. So just to give just 1 minute. I'm facing some difficulty in sharing my screen.
Sir, it is visible, sir.
But the slide is not changing actually. Yeah. Okay. Yeah. Has the slide changed at your end? Okay. Am I audible now?
Yes, sir.
Okay. So just to give an overview of CDOT. So CDOT was established in 1984 as an autonomous telecom R&D center under the Department of Telecom, presently under Ministry of Communication, Government of India. So we have two offices in Delhi and Bangalore, and we are focused in multiple technological domains, including optical access and optical core networks, 4G and 5G wireless networks, Wi-Fi and network security, AI and M2M based solutions. And also we have started doing quantum communications for both quantum key distribution QKD and post-quantum cryptography called PQC in the last 3-4 years. And recently the National Quantum Mission has been launched, and IIT Madras in association with CDOT has been selected as the thematic hub under this mission in the quantum communication vertical. So we are leading a technical group under this post-quantum cryptography as well. So that's the brief about the CDOT. Then just to give an overview of what I will talk today, there will be an introduction. Then I will focus on why do we require the quantum communication at all. So what are the challenges that we are facing with the classical cryptographies? Then how QKD works, what are the network topologies in QKD? And then I will focus some of the challenges in deployment, because ultimately the product needs to be deployed in the field. Then I will showcase some of our products that we have developed in CDOT. And then I will conclude with some applications of this technology. So as today is the National Technology Day, you are all aware that we are going through something called second revolution of quantum technology. So we are already using different products that uses quantum mechanics in some way or other. So like you are all aware that lasers are there, solar cells are there, and MRI machines are there. They all use some sort of phenomena that uses in the background the quantum mechanics. For example, the lasers use stimulated emissions, the solar cells use photovoltaic effect, and the MRI machines uses magnetic resonance. And all these things were there for many years, and they use some form of quantum mechanics. Now with the progress of technology, with the progress of the process, now we are seeing some new applications in terms of computing, communications, and sensors that have multi-fold potential to have new use cases, and that can transform our lives in many ways. So in view of that, United Nations has declared this year 2025 as International Year of Quantum Science and Technology, because this year marks the 100th anniversary of quantum mechanics. So different activities are being organized all across the world to mark this year 2025 as the International Year of Quantum Science and Technology. So quantum technologies have 4 verticals. So these 4 verticals include quantum computing. So quantum computing includes extreme high-speed computation. Like presently we are having supercomputers, but when it comes to quantum computing, it can solve many problems that is currently unsolvable. So it will have effects in financial market, drug research, genetics, your problems related to financial trading. So everything in different molecular research in chemistry. So many problems that are currently not solvable in a considerable amount of time, that can be possible when we have a full-fledged quantum computer. Then the other application is quantum communication, like how we can securely communicate our data across the internet. So there are 3 technology candidates that I have listed here. One is called quantum key distribution. So I will talk more on quantum key distribution because this is the most practical areas of quantum communication. Then there is quantum teleportation and quantum internet. On the other hand, we have quantum sensing. So quantum sensing deals with ultra sensitive sensors, like that can be magnetic sensor to sense the magnetic field, that can be sense for the gravitational field, and they are extremely highly sensitive, that cannot be possible with the classical sensor that we are presently using. And one application of this can be like quantum GPS, so that you can have GPS in such areas like in submarines or in underground, but there is no GPS signal is available, or there is some jamming type of thing is there. So quantum sensing has very good applications in defense and military type of things. Then another application will be high accuracy clocks using the quantum phenomena. The 4th vertical is quantum materials. So quantum materials deals with the materials that uses some form of like quantum dots or quantum phenomena that uses to get the components like high density storage, very low power device or superconductors. And all these other 3 verticals will be a beneficiary for the advancement that will be done in the quantum materials. And in line with these 4 verticals, National Quantum Mission has also come. So over the next 7 years till 2031, they have decided these 4 verticals to have 4 thematic hubs in these 4 verticals of computing, communication, sensing, and materials. And they have identified some educational institutes, mostly IITs, and the CDOT is there in quantum communication. So they will be leading 4 verticals, and there are 4 thematic hubs. Different research projects have been selected, and try to develop different technologies in all these 4 verticals. And the estimated budget they have quoted is around 6,000 crores for the next 7 years. So India is definitely progressing in a right direction for this quantum revolution too. And as I talk about quantum communication today, so there are 4 main technology candidates that are there in quantum communication. So first thing as we talk is called the quantum key distribution, or QKD. So QKD is basically a method of key exchange between 2 communicating parties. So I'll talk more on this in the subsequent slides. Then comes quantum secure direct communication. So this field is not that much developed as of now. So this involves the direct and secure transmission of messages over a quantum channel. So QKD is basically generation of keys. There is no data transfer, only the key exchange is there. But when it comes to QSDC, it involves sending messages using quantum phenomena. Like you are sending qubits in the term of photons, and we are exchanging some message. So that is called QSDC. The third thing is that quantum teleportation. So quantum teleportation means sending one quantum state or quantum bit or qubit from one place to another. So the qubit does not move the place. So only the thing that some classical information is exchanged, and the qubit, say it is now in Delhi, it will be transported to say Andhra Pradesh. So that's called quantum teleportation. But these QSDC and quantum teleportation fields are relatively immature compared to QKD. Because there are multiple protocols are there for QKD, multiple works have been done. Many companies are developing field-worthy products. The 4th thing is that the quantum internet. So currently we are using the digital internet. So here the digital computers are connected using the networks, and we can communicate over internet. But when we have a quantum computer in future, so they need to be connected using a different type of like network that is called the quantum internet. So this is how the future quantum computers will communicate with each other. So that's the flavor of quantum internet. And this quantum internet will use all these 3 technologies: QKD, QSDC, quantum teleportation, and there are other technologies like entanglement, swapping, and others. So everything will be used in quantum internet. So now I'm coming to like basics of cryptography. So all of us know that why cryptography is required, because we are sending some messages over a public channel, and we need to protect the privacy. Like we are sending some message that this is the message. we are encrypting it using a key, and then we are making it a ciphertext, and at the receiving it, we are decrypting it and getting back the original message. So the key is the main thing that needs to be protected, because if the key gets tampered, then your secrecy is not there. And you are all aware that cryptography can be broadly classified in two categories. One is called symmetric key, other is called the asymmetric key. So the main difference is that in symmetric key, we are having same key for both encryption as well as decryption. And for asymmetric key, there is a public key that is used for encryption. And then at the receiving it, there is a private key that is used for decryption. Now, currently what we are doing, we are using both of these technologies together. So what we are doing presently, we are encrypting our keys using public key cryptography, then doing the key exchange. Then we are using symmetric key to actually encrypt our data, right? So presently we are using, say, suppose DP-Hellman to exchange keys for AES-256. Then we are doing AES-256 to encode our actual data. Why this is happening? Because asymmetric cryptography has more complex due to its algorithms and all these things. So we cannot encrypt the data using this public cryptography. So that we need symmetric cryptography. But the issue is that once we have a cryptographically relevant quantum computer, this asymmetric key will be broken. But so if this is broken, then you will get the keys for your symmetric key cryptography, and then you will get your data. So this communication will no longer be secure. Now question comes whether this symmetric key cryptography is secure when we have a quantum computer. So it will be secure provided your key length is 256 bit, because if you use AES-128, it will not be secure. It can be broken by quantum computers, but if you use AES-256, it will be secure. So we need to migrate to AES-256 at least. So key length cannot be less than 256 bit once we have a quantum computer. So as I told, that asymmetric key can be broken. So we need some mechanism to distribute the keys for symmetric cryptography. So suppose we are communicating between New Delhi and Andhra Pradesh. So how do we have same key at both ends? So that's why QKD comes into picture. So we need some mechanism to distribute the keys. That is currently being done by public cryptography, and it is no more secure. So what are the challenges? Just to list that challenges is that presently if there is any intrusion in your system, there is no ways to detect, because some intrusion can happen in your system and they can steal your data. And until and unless they give some signature or make your data public, you cannot detect actually. The second thing is that the asymmetric cryptography is based on certain assumptions, like these are based on mathematically hard function that cannot be computed by even the most sophisticated classical computer. But when we have a full-fledged cryptographically relevant quantum computer, that type of assumption is not valid. So I will show in subsequent slide why it is not valid, that how that classical public cryptography will be broken. Then there is another type of thing that is called brute force attack on cryptographic keys. Like brute force attack means suppose you have a 8-bit keys and you are trying 2 to the power 8 combinations one by one. So that type of attack can also be done very easily once you have a quantum computer, because they are very efficient in terms of timing. And also, as I told earlier, asymmetric cryptographies are slower compared to symmetric cryptography because due to their algorithms. Now, the basics assumption of classical public key cryptography is that prime factorization of an integer. So there is I have given a small example of how prime factorization look like, but in reality, the number is very large, and as the number goes, the timing complexity is of the order of sub-exponential. So at present, your data is secure and it cannot be taken away by any eavesdropper. But there are two algorithms. One is called source algorithm. It was discovered by Peter Shor, and later it was this algorithm was modified to be implemented in less number of qubits by a Chinese scientist called Schnorr. So these two algorithms can make this sub-exponential timing complexity to polynomial timing complexity for prime factorization. So you can easily now break this problem, prime factorization, using a quantum computer once we have. So your classical cryptography is no longer secure. Now, as I told of brute force attacks, so brute force attacks generally have a timing complexity of the order of n. But there is a person called Lab Grover. He was an Indian person passed out from IIT Delhi. So he has come up with something called Grover's algorithm that can reduce the timing complexity for this brute force attack from of the order of n to of the order of root n. So that once we have a quantum computer, using these two algorithms, our data might be at risk because the public encryption can be broken. Now there is a famous scientist in Canada. His name is Dr. Michel Mosca. So he has come up with some inequality. So this is called Mosca's inequality. So this Mosca's inequality tells that each data has some lifetime. Like suppose you are having a OTP. That OTP in your mobile has some limited lifetime. So it is say around 2 minutes. But if it is a defense secret or strategic information, that can have a lifetime for say years. So D is the lifetime of a data for which it needs to be kept secure. Then another parameter is called the time T. T is like suppose we are using today classical systems and we need some time to migrate this classical system into quantum system. Say it will take say 5 years and your data lifetime is say 2 years. So 5 plus 2 is 7 years. Now if you know that quantum computer is arriving in say suppose next 5 years, that is the parameter QC, then we are in danger. So if this is D is I have taken 2 years, T is 5 years, so 2 plus 5 7. And if QC is say 5 years, then we are in trouble. So because when the quantum computer will come, they can easily break our data. So this is the famous inequality that he has come up with, and it is widely cited in multiple literatures. And the thing is that there have been multiple experts. They have claimed that we are already in the danger zone because this inequality has been broken in 2017, and we are currently in 2025. So if you see, there are multiple reports that are coming in news and literatures that many people are claiming quantum supremacy or quantum advantage. So what does this term means? So this term means that if you have a quantum computer, so you can do something that cannot be done using classical computer. So that is called quantum supremacy. And if this that what you are doing, if this is a purposeful thing or that has some advantage in your daily life, then it is called is quantum advantage. So that is a relevant operation. So if you do something just for the sake of computation, you do something that is called quantum supremacy. But if it has some relevant application, it is called quantum advantage. So basically doing something that is not possible with the help of a classical computer. So in 2019, Google claimed that they have done some operation in just 200 seconds compared to 10,000 years of a supercomputer. So this is a significant gain in terms of speed. A Canadian startup, JNTUGV, in June 2022, they have made similar claims. So they have done some operation in 216, like they have done something in 36 microseconds compared to 9,000 years in a classical computer. And in October 2023, there is a more than 1,000 bit, like it is to be right, it is around 1225 qubit quantum computer was announced by Atom Computing. And if you see the recent news, recently both Microsoft, Google, IBM, and there is a Chinese company called USTC. So they are all working on various forms of quantum computing chip. So they are Microsoft is coming with Majorana 1, Google has come up with Willow, IBM Heron R2, and Amazon Ocelot. So they are all these chips are making being used for making for like quantum computing easy. So currently they are in the very very early stage, but they are all these companies are working to develop this quantum computing chips. So the threat from the quantum computers is getting real because we are now heading towards having a full-fledged quantum computer, and no one knows when it will come. So now I will talk about quantum key distribution in detail. So why quantum key distribution? So this is because we have two communicating parties here. So they are traditionally called Alice and Bob. So they will be connected using two channels. So one is called quantum channel. Quantum channel is unidirectional. As you can see, it is from Alice to Bob. So this channel will be used for sending the single photons from Alice to Bob. And there is another channel called classical channel. So this channel will be used for synchronization and other post-processing steps. So quantum channel is unidirectional. It carries the single photon. So it is very weak in power. And classical channel is normal Ethernet communication link. So there is nothing new in this channel. So as I told, it is based on quantum mechanical principle. So mainly Heisenberg's uncertainty principle and no cloning theorem. No cloning theorem means you cannot copy an unknown quantum state. Then this channel, both this channel can be implemented through optical fiber, free space like FSO communication, free space optical communication, or satellite based link. That is also an extended version of free space link. And currently, this fast QKD protocol that was presented in a conference in Bengaluru by two scientists called Charles Bennett and Giles Brassard, and it is called BB84 based on their surname and the year of invention 84. So currently in CDOT, we are working on fiber-based QKD. That is, we are using the optical fiber as these channels. And ISRO is working on satellite-based QKD, and different other organizations are also involved. So I will talk mostly more of on fiber-based QKD in the subsequent slides. So as I told, QKD is a method of secure key exchange, and that security is guaranteed by the fundamental principles of quantum mechanics. And the main flavor here is that if you try to tap or if you try to listen to the channel while the keys are being generated, then the system gets alarm immediately. So there is no thing that can be hidden. The attack cannot be hidden. So it is an information theoretic security. Because there is no assumption, as it was in the case of public cryptography, that certain mathematical problem cannot be solved. So this is not the case here. It is the mathematical proof can be derived for the theoretical security of QKD. And there are some statistics that have come from IBM that if it was a data breach in 2020, so the average financial loss was around 3.86 million. And in 2024, it has gone up by almost 25%. So this like your data is now very important, as you all know, and that the financial figures also support this type of assumption. And there is another market research report that they claim that the global QKD market is going to touch around $3 billion by 2030, because all the major economies are investing heavily in quantum technologies in all these 4 verticals. So just to demonstrate how a quantum key distribution system works. So this is your present network. Like we are having an encryptor, then we are encrypting the plain text message to a ciphertext. We are sending it via some channels, and in the receiver end, we are decrypting it. So this is our traditional encryption system that we are currently using. So when you are talking of QKD, we are adding an extra layer that is called the quantum layer. So we are having Alice and Bob at both ends. So they are connected using 2 channels. One is called quantum channel. The other is classical channel, as I told, and they together are called the QKD link. And this layer is added. Now the encryptor will request the keys from this QKD module, and then this QKD module will supply the same symmetric random key at both the ends. So that's how the QKD works. So this is the basic architecture of a point-to-point QKD link. So this interface, this vertical interface, is standardized by ETSI. So any encryptor that supports the ETSI standard can be interfaced with a QKD system. But there is there is no standard that mandates that one QKD module, say of vendor 1, and other QKD module at Bob's side of vendor 2 can operate. So there is no interoperability in the horizontal direction. But in vertical direction, any encryptor can fetch keys from the QKD module. So this interface is standardized, but this interface is not standardized yet. So if you need Alice from vendor 1, you will also need to have Bob from vendor 1. So this is a vendor lock thing, Alice and Bob, but this encryptor, you can have any vendor encryptor. So this is the point-to-point topology, and ITUT has in the standard Y.3800 series. So they have extended this point-to-point topology into multiple complex topologies, say using one optical switches, and this is the mesh type of topology. To support this complex type of topology, CDOT has worked with 3 topologies. So one is called trusted relay. So the trusted relay is needed because here we are having 2 nodes, Alice and Bob. They are connected using optical fiber. Now this fiber channel has some loss. So due to loss, we cannot go infinitely. So we need, because the photon that you are sending from here, that will be ultimately absorbed in the channel, and only a fraction is received at the receiving end. So to avoid that, after some time, it will be only noise. So to avoid that, we need some trusted relay type of thing. So here, this trusted relay is used to have a longer distance of communication. Suppose this link was 150 kilometer. So using this trusted relay type of thing, we can go up to 300 kilometer. So any 2 nodes in this link will have keys to communicate with each other. So that you can see that node A and node B communicate using that red key. Node B and node C can communicate using the blue key, and node A and node C can communicate using the green key. So any 2 nodes in this chain can have same secure random keys, and they can communicate. So this chain can be increased by adding such trusted relays more and more. The other topology that we have worked on is called a ring topology. So ring topology is that if here I have shown 4 nodes, they are connected in a ring fashion. So if one link is broken, suppose K12 link is broken due to fiber cut or something, then these site 1 and site 2 can still generate keys using the trusted relay through site 4 and site 3 using the trusted relay. So this is a like this is a redundant path is there. So this is suitable for ultra high reliable service what is required for, say, example, in defense, where we cannot have any downtime. So this type of application can be done there, ring topology. The third topology that we have come up and we have filed a patent on this also. So this topology is called a fail-safe dual star topology. So why it is significant? Because in Bob node, we are having the single photon detectors, and these single photon detectors are very costly item. They are presently imported, and this comprises of a significant amount of amount in the bill of material. So we are sharing this Bob node among multiple alleys. And all these alleys 1, 2, 3, 4 will generate keys in a like time division multiplex fashion. So first alleys 1 will generate keys, then alleys 2 will generate keys for some time, then alleys 3, and then alleys 4, then again alleys 1. But the thing is that in this star topology, what happens? The Bob becomes a single point of failure. So if Bob fails by chance, so all this network will go down. So to prevent that, we are using that one Bob is active and another Bob is standby mode. So that is why it's called fail safe. So in normal operation, Bob, the active Bob will cater to half of the alleys, and Bob standby Bob will cater to half of the alleys. And once by chance, if any Bob fails, then the other Bob will take over all the 4 alleys. And this way, the security, like the ability of the key distribution will be made higher, and it's called fail-safe dual star topology. So QKD can be deployed using any of these topology or a combination of these based on the requirement. And these are the classifications of the quantum key distribution protocols based on decoding method of quantum states architecture. So based on decoding method, one is called continuous variable. So here we use the position or momentum. Like these are all continuous variable, and the other one is a discrete variable, which is based on the phase polarization. Say phase can be 0 or pi. Polarization can be horizontal and vertical. So they're all discrete variables, and time pin can be, say, for early or late. So these are called discrete variables. And one subset of discrete variable protocol is called distributed phase reference. So I'll talk more on this in the subsequent slide. And based on the architecture of protocols, there are 3 types. So one is called prepare and measure. So what happens in prepare and measure? So Alice prepares the quantum states and it sends to Bob, and Bob measures it. So it is a 2-node system, Alice and Bob. So Alice acts as a transmitter and Bob as a receiver. In the measurement assisted system, what happens? There are 3 nodes involved, Alice, Bob, and Charlie. So Alice and Bob both acts as the transmitter, and they sends the quantum state to a central node, Charlie, and Charlie makes the measurement. So, but the protocol is designed in such a way that Charlie will not have a clue of the keys that are being generated. So that's why it's called measurement assisted protocol. The other protocol is called entanglement based protocol. Here what happens? Alice and Bob, earlier it was transmitter in measurement assisted. So now they will be act as a receiver, and Charlie will be the transmitter. So Charlie will prepare an entangled state. So one part of the entangled state he will send to Alice, other part will be sent to Bob, and they will generate the keys. Here also again the Charlie will not have any clue of the final key that will be generated. So these are the classification. And while designing a QKD system, you can choose different protocols, but there are some things that you need to keep in mind. So the first thing is that how it is easy to implement on us, that is the hardware that are currently available. How many detectors are required, because detectors are costly, as I told. What is the rate of key generation, because different application needs different key rate. And what are the number of nodes, because prepare and measure have 2 nodes, Alice and Bob, and while as measurement assisted has Alice, Bob, and Charlie, entanglement base also has Alice, Bob, and Charlie. What is the maximum distance supported between 2 nodes? Because some protocols support around, say, 150-200 kilometer. Some protocols can go up to 500 kilometer. And what are the immunity from various quantum hacking activities? Like quantum key distribution is information theoretically secure, but some hacking can be done that have been there in the literature, that some hacking can be done using the imperfection that is there in your device, because your device is not fully quantum. They are classical device. So you can have some side channel attacks exploiting the imperfection in the device. So we have in CDOT, we have designed the QKD system using 2 protocols. So one is called the coherent one-way, the other is called the differential phase shift. So this is the basic block diagram of a coherent one-way QKD system. So here we have, it is a prepare and measure type of protocol, or you can call it a distributed phase reference protocol, because here we are using the phase reference between 2 consecutive pulses. So how it is working? So in the Alice side, we have a laser. So this laser is a very narrow line width laser source, and this system is operating at C band, that is the 1550 nanometer. And we are having a lithium niobate intensity modulator. and we are having a onboard quantum random number generator. So it is generating some random number and it is giving to the FPGA on board. Then FPGA is driving that random number through pulses, making pulses and driving the intensity modulator. Then we are having the pulses. And how we are encoding bit 0, bit 1. So for bit 0, we are having 2 slots. If the photon is there in the second time slot, it is called bit 0. And if the photon is there in the first time slot, it is called bit 1. And if photon is there in both times, so it is called a decoy state. So decoy state is used to check if there is any eavesdropping on the channel or not. So these bits are then attenuated in such a way that the mu, that is the average photon, is less than 1. So typically the value is 0.5 in our COW system. So the mean photon number of 0.5 means that you are sending 10 pulses, for example. The 5 of the pulses will not have any photons. So the remaining 5 will be vacuum and 5 pulses will have photons. So this is the basic architecture of a Alice. And in the Bob side, we have 2 single photon detectors. So they will detect the photons, and the post-processing will be happening in the FPGAs. And use this SPAD1, that is the single photon avalanche diode, that will be used for SPAD1 will be used for detecting the keys, and this SPAD2 will be used for detecting any eave, that is the eavesdropper present in the channel. So that's how this COW protocol works. In case of differential phase shift, earlier we are using the time slots as early and late, because if you see that bit 0 and bit 1 was based on the time slots. So if photon is there in the second pulse, it was bit 0. Photon is there in the first time, so it was bit 1. In case of time slot, here we are using the phase. So here one extra module will be added in Alice, that is called the phase modulator. So it modulates the phase in 0 or pi, again based on the data that we are receiving from the quantum random number generator, QRNG. So here in the Bob side, we are having a 1-bit delay line interferometer. So this is the bit interval T, and you can here also we are having 2 detectors, single photon detectors, and as they are 1-bit delay line interferometer, you can see that they are shifted by 1 bit, and they will now interfere. And if the phase difference is 0, so one SPAD will click, and if the phase difference is 5, the other detector will click. So that's how the keys are being generated here. So it is basically the phase relation between 2 consecutive bits. So that's how the DPS protocol works. Here the mean photon numbers is also less than 1. It is typically around 0.2 in case of DPS. So what happens, how the keys are generated in QKD? So first, when Alice and Bob, they are powered on, so they authenticate each other's. Like Alice checks whether this is the intended Bob, and Bob checks whether it is the intended Alice that I want to communicate. So there are certain mechanisms for this classical channel authentication. Then this qubit transmission and synchronization happens. So first you need to have the synchronization, because we need to have a common time reference for both Alice and Bob. Then we transmit we transmit the qubit, that as I shown in the previous slide, using either phase modulation or using the time position in case of cow, and the phase in case of DPS. Then the raw key is generated and we perform the shifting. So here you can see the spelling is not wrong. So it is called SIFTING. Shifting means filtering out. So suppose Alice sends 100 photons and to Bob, and there is some loss in the channel. So 100 will not reach in the Bob. So Bob will disclose at what time he has received some photons. So that suppose Alice had sent 100 and Bob has received 20. So Bob will send the time values of these 20 photons, not the exact values 0 or 1. They will send the time values T1, T3, T5 like this. And then Alice will discard the remaining bits. So that process is called shifting. And then if that's after shifting, we check the quantum bit error rate. Like if 20 bits have been received, what is the error rate in that? If the bit rate is less than threshold, we abort the more than the threshold, we abort the communication because the channel is not secure. And if the error rate is less than the threshold, we proceed to the next step, because we need to there is error, so we need to perform error correction. So presently it is done by low density parity check, and after that we perform some privacy amplification to compress the key, because during error correction someone may listen, because this error correction, shifting, and these steps are done in the classical channel. So there is no quantum security in there in the classical channel. So anyone can listen. So to avoid that type of information leakage, we do the privacy amplification to receive at the final secret key. So these processes continue multiple times, and you can keep on accumulating the secret keys. So as I told, QKD can have multiple media: fiber, free space, and satellite. Fiber is the most commonly used, but free space and satellite is also getting popular. The quantum channel is best performance can be obtained. We are using have a dark fiber. Like there is no other wavelength in the fiber. We are only sending the quantum signals using that fiber. but while you are going to deploy in field, not always the field of dark fiber is available. So we need to multiplex with other data carrying signal, and that will be at high power. So this high power signal will corrupt the quantum signal. So the distance get limited, and it's called a multiplex system. But it is doable. We have done this, but till up to 50 kilometer. But in case of dark fiber, it can go up to say 150 kilometer. So there is a significant reduction in that time. So in length, sorry. And then wavelength can be in either in C-band 1550 nanometer or in 1310 nanometer and in 850 nanometer. It is mostly used in free space 850 nanometer. And the detectors can be either single photon avalanche diode, so the red one, or it can be a superconducting nanowire single photon detectors, this big one. So this is a very bulky system. It cannot be shifted easily, but this can be put inside a box. So it is the most commonly used. But if you are using very high sensitive detectors, so these are, you can see all these parameters are very high compared to the SPAD. So this is costly, but the thing is that it required cryogenic cooling, and it has a vacuum pump and helium compressor along with it, which is not shown in this picture. So this is a very costly item. It cost around say 2 crore, but this is a miniaturized system, and performance is less, but cost is also less. So that's the main difference between these two detectors. So we are using that SPAD in our boxes presently. And this SNSPD is used for only the lab experiments. So now I will not go in detail about the QKD standards. So if you are interested, you can go in this, look at this standards. So ITUT is leading the standardization for QKD. So they have come up with different standards and these standards are evolving each day. So they are publishing new standards. So currently they have gone up to 3817 starting from 3800. So these standards talk about QKD network, QKDN. So how QKD network works, what are the different layers, what are their functions. So these standards deals with this. Then there is another study group, they work with QKD network security and the QKD network application security. So these are the 4 standards for that security perspective of the QKD network. Then ETSI is also working in different security related and interfaces for QKD. The most important is that, as I told, the vertical interface, that is the key supply, is called the GSQKD014. So any router that supports this REST-based interface, we can fetch keys from any QKD system. So this is the most used standard for key supply to any encryptor or any router device. The other organization is called the ISO-IEC. So they have come up with 2 standards to test the security of a QKD system. Like you have designed a QKD system, but how do you know it is actually secure? So this type of test they have mentioned in these 2 standards. And in India, there is a organization under the Department of Telecom called Telecommunication Engineering Center. So they have come up with TEC-GR, generic requirement in 2022, and the test guide for 2023. So in India, any vendor who is developing that QKD systems, they need to comply with this TEC standard, and they need to have some certificate from TEC. So while you are developing and deploying QKD system, there will be multiple challenges. Like first challenge will be like lack of dark fiber. As I told, that it will be the best performance when you are using a dark fiber for the quantum channel, but it is not always available. The second thing is that the fiber that is already deployed have different cuts and splices, so the loss is very high. So you cannot go in lab. You can go up to 150 kilometer on a say using 0.2 dB per kilometer, but the actual loss in field is very high. So it is around 1 dB per kilometer. So again, the rodents are there. So rodents cut the fiber in some places and makes the communication unavailable sometimes. The second thing is that these single photon detectors work in air conditioned temperature. So you need to have a temperature less than 25. So which is not the case in India in most of the year. So we need to have air conditioning all the time. And the solar radiation, if there is a fiber and solar light is falling on this, so this count as a dark count, like a noise on the detector. So this type of things we need to avoid. Again, as I told, there is no standards for Alice and Bob from different vendors. So that's the issue at present. There is lack of awareness among different stakeholders, like why quantum security is required, when should we deploy it. So although this awareness is getting more and more, like they are becoming more and more aware day with days, and National Quantum Mission is working on this direction. And there is a shortage of workforce to work on this quantum technology. So that's why they have now launched a syllabus, and even in the undergraduate curriculum for quantum technologies, AICT and DST, they have come up. And there is, as I told, ISO-IEC has some standard, but in India, there is no, till date, there is no agency that confirms that your QKD system is secure. TEC has some guidelines, but that is not sufficient for having a security certification for your QKD system. So now I will talk some of our solution that we have developed. So this is our QKD system. This is a two-box solution, prepare and measure protocol, Alice and Bob. So as I told, we are using two protocols, differential phase shift and coherent one-way protocols. And as I told, this TEC has come up with a generic requirement, TEC-GR. And we are the first in India to have the technology approval for from TEC for our QKD solutions. And this is the certificate of approval from TEC. So this is the point-to-point QKD system. These are the different specs. So two protocols we support. The quantum bit error rate is less than 5%. So if the bit error rate is more than 5%, the keys are not generated. So your channel will not be secure. So this is acts as an indicator of that your channel is not secure. The secure key rate is around 2 kbps at 23 dB loss. So 23 dB is roughly 115 kilometer on a lap fiber and greater than 1 kbps for COW protocol. But the supported channel loss is around 30 dB. So we can go up to 30 dB, say up to 140 kilometers fiber spool with the avalanche diode based detector. And if we use superconductor detector, we can go up to 220 kilometers. So as I told, we are using C-band 1550 nanometer. Key transfer to any router or encryptor will be through USB or Ethernet interface. That is the RJ45 interface Ethernet. The operating temperature is 10 to 25 degrees centigrade. So we need to have an AC so that this system operates properly. Power consumption is nominal around 250 watt and it works in standard AC supply. And it is a rack mountable solution. You can also put it on a table. So these both hardware design, like the printed circuit boards, mechanical, electronic packaging, everything was done in-house. In FPGA, all this key distillation engine, like the error correction, privacy amplification, true random number generation, all these things we have done in-house in FPGA. Software from the ITUT stack we have developed in-house. So we have implemented the QKD network controller, QKD network manager, and the key manager. So with our system comes with a graphical user interface that will help you to control different parameters and see the performance of the systems. So all these things are developed in-house. The only thing is that the electronic and optical components like the lasers, modulators that are not available in India. So we need to import them from abroad. So this is one of the systems that we have developed to address the areas where there is no dark fiber. So here we have multiplexed the fiber using WDM, like wavelength division multiplexing. So quantum channel of QKD, classical channel of QKD, and 100 Gbps data stream we have multiplexed in a single fiber using WDM, and we can reach up to 50 kilometer using this type of system. So we have published a paper on this in ComSnet 2024. So you can have a look how this system works. And recently we have come up with another system. So earlier system was using two fiber. One is in the RX direction, other is in the TX direction. So this system has been modified now to have one single fiber for both the directions. So here the quantum channel, classical channel, TX, RX, and 100G TX and RX, both are all these 5 things are in a single fiber, and we can go up to 50 kilometers. So the fiber requirement is further reduced, but the only thing is that it's suitable for metropolitan area application and cannot go beyond 50 kilometers because the noise from the high power signals corrupt the quantum signals. The latest development that we have done is called the MDI QKD, or called measurement device independent QKD. So here we have 3 nodes, Alice, Bob, and Charlie. So as I told, in measurement assisted protocols, Alice and Bob acts as a transmitter and they send some quantum states to the Charlie. And Charlie does the measurement and announce the result to Alice and Bob using the public channel. So why it is required? Because there are some side channel attacks that called detector blinding attack and time shifting attack. These attacks are reported in literature. So they are very difficult to like implement in real life, but the attacks are there. So to address this type of attack, MDI QKD system can be deployed. So this is the lab setup of our MDI QKD system. So here you can see this is the Alice unit. This is the Charlie along with the SNSPD is here. You can see if the screen is clear. So it is working with the SNSPD because the key rate with SPAD is very low in case of MDI QKD. So it is due to the protocol. And here is the Bob unit. So it supports up to 100 kilometers of distance. Alice to Charlie 50 kilometers and Bob to Charlie and 50 kilometers with SNSPD. Now we have come up with one setup that is called a EVE simulator. So the EVE simulator goes between in the quantum channel between Alice and Bob. So this simulator main function is that it simulates some of the quantum side channel attacks. So it is not an actual EVE. It is only simulates the attacks. So it simulates the effects of the attacks. So we have implemented 3 attacks. One is called the PNS attack. photon number splitting attack. And so we randomly change the phase of the quantum signal. The second is called the Trojan horse or spurious signal injection. So we generate some laser signal and inject it into the fiber. And the last thing is the fiber tampering. So here, what we are doing, we are increasing the loss of the fiber using some variable optical attenuator. So in all these three attacks, if you activate, your quantum bit error rate should go up. So that is an indicator that your system is actually performing according to the principles of quantum mechanics. So if someone has developed some QKD system and he wants to check the performance, how it is resistant to different side channel attacks, so he can use this type of instrument and check whether the system is actually secure or not. So we have done different multiple field trials in done deployments. So we are the only public funded institute in India that have a QKD solution deployed in the field with live traffic. So we have developed deployed one link between Sanchar Bhavan, that is the Department of Telecom, and National Informatics Center in New Delhi. So all the traffic between these two offices are encrypted using the C.dot router, and the C.dot router takes the keys from the C.dot QKD system. So this system is running for now almost more than 2 years. And this link has also been tested by TEC as part of the technology approval process. And we have done multiple field trials in like in Indian Army network and Indian Air Force network. And the thing that I want to highlight here is that we have given our setup to multiple educational institutes. So we have given to JIT Noida, JIP Institute of Information Technology in Noida in February 2022. We have given the setup to DY Patel University, Mumbai last year, and also given to NSUT Delhi, Netaji Subhas University of Technology, Delhi in this year. And we have given one link to that metro area quantum access network of IIT Madras. So this link is there at ARNet India. So one link has been deployed in Macan network to check the interoperability of C.dot QKD and IIT Madras QKD link. So we have given to 4 educational institutes, and they are using our setup to perform various experiments like they are publishing multiple papers in different journals, and they are using it for teaching that students. So this is that educational setup that I am talking about. So this is Alice and Bob. The if simulator is optional. So if you have budget, you can go for this if simulator. So this is a totally indigenous design. It is cost effective, and we provide the supports, and this is compliant with the AICTE's model curriculum. So whatever has been launched, so I can share the compliance if required. So we support that curriculum, and different type of experiment you can do. Currently, the system that we are offered is a cost-effective version, that is a COW protocol, and it can be later upgraded to full-fledged COW or DPS QKD system if your budget is higher in future. And also you can also opt for if, that is an optional thing. So this type of system can be used for academic setup to know how the secure keys are generated, how QKD works. You can develop your own custom encryptor algorithm to take the keys from QKD system and encrypt the actual data. So different type of experience you can perform and feel a first-hand experience like how this quantum phenomena is generating the secure keys. So this system cost around say 80 lakhs, and no lab setup is required. Only the thing is that you need to have some AC type of thing in the lab to operate. Say just only AC is required and 230-volt supply. These are some of the patents that we have been granted in this field. One patent is pending, and some of the research papers that have been published. If you are interested, you can look at these papers. And this does not include the papers that are published by other institutes using our system. So they have also published some papers in reputed journals. So they are using to evaluate the performance of our system in the different conditions. We have given the transfer of technology to multiple institutes and like multiple manufacturers in India. One of them is a PSU, Electronics Corporation of India. 2 startups are there, Skytel Alpha and Chip Spirit, and there is one private company called New Age Instruments and Materials. So they are our transfer of technology. So in case of any large scale deployment, they bid for any tender and they manufacture the system and deploy. And also we are listing our system in the government e-marketplace, GEM. So it will be there in next 15-20 days. So this is the some of the awards that we have received for the QKD solution. One is the Aegis Gambret Award last year, and Technology Sava Awards this year in enterprise security category. These are the typical application areas for QKD. So first thing is the data center interconnect. So how do you secure your data center communication? How do you secure your government or strategic communications, power grid communication? Banking network is a key area, banking and defense, and then telecom networks and pharmaceutical. Because every network where the privacy is a concern, QKD is the solution because the quantum threat is real and it is becoming more prudent day by day. So this is the typical example of a network, like you are having, say, suppose this is a 4 offices or 4 university branches, and they are connected using an IP network at present. So, and now you need to upgrade it using a quantum network. So you do not need to change the whole network. Only is that you need to place the QKD nodes at the gateways, and then you need to connect it using the QKD links. So these then you can upgrade it with the quantum security. So your inside network will be remain same. Only the outside network will change. And based on this fiber connectivity, you can easily upgrade to quantum security. So just to summarize, we have developed the field deployable QKD solutions, and we are the first to receive the technology approval from Telecom Engineering Center. And we are also working in different other technological verticals like post-quantum cryptography, 4G, 5G, and AI. And as I told earlier, that CDOT is now the hub under National Quantum Mission in the quantum communication vertical. And we can provide customized solution like for your educational setup or if there is any deployment need, we are okay to work with the academia to provide different customized solution addressing your budget constraints so that you can use this setup for different educational purpose also. So that's all from my side. I'll be happy to answer any questions from the audience.
Thank you, sir. Thank you, Arka Mukherjee, sir, for your highly informative and thought-provoking session on fiber-based quantum key distribution systems and CDOT initiatives.
Yeah.
Do you have any questions? Please raise your hand. I will unmute your mic.
Yeah, sir, you have asked a question about the difference between quantum channel and classic channel, right?
Yes, sir. Yes, sir.
Yeah. So the thing is that these are both channels are implemented using, say, single mode fiber or free space, depending on whatever QKD you are using. So if you are using fiber-based QKD, both of these channels will be using optical fiber. But the main difference is that quantum channel is a unidirectional. It is from Alice to Bob, or so it will carry the single photons. That is the qubits from Alice to Bob. These qubits will be modulated in terms of phase or in terms of, say, pulse position. As I told, in case of DPS, it will be phase.
Okay, and we connect with the different hardware, sir.
Sorry.
We connect with the different hardware, classical channel,
no, they both both Alice and Bob will be connected using 2 channels. One is quantum channel that is carrying the single photon states, and the classical channel is normal Ethernet communication. So that is there already. So that is for the synchronization purpose and that error correction purpose.
Okay. Sir, I have another question.
Yeah.
So how it is for the IoT communications, sir, because IoT devices are very limited constraints. We have very limited memory and very limited CPU.
Sir, for IoT, QKD cannot be used actually, because the thing is that IoT devices are very small, right?
Yes.
And they operate in a very energy constrained setup. So they cannot actually take keys from QKD. So for that thing, QKD is not suitable. It is mainly suitable for, say, suppose you have a communication link between, say, Delhi to Mumbai. So you need to secure that intercity link, or there is a banking head office there, and there are multiple branch office. So you can secure the communication between there, or there are multiple government establishments there. Your JNTU branch 1 is there in, say, suppose Vijayanagram, another branch is there in Kakinada. So you need to secure the communication. So this type of application is there.
Okay, sir. Okay.
Yeah.
So for the limited communication, it is not possible.
IoT, because this is the power is limited and they are all like wireless type of device. So QKD requires dedicated hardware, so it might not be feasible for IoT application.
Okay. Sir, another person asked the question. Sir, how to store qubit and quantum data?
That quantum data that you are taking is that we are generating that random numbers. So suppose you are having generating a pulse, right? So you need to modulate 0 and 1. So 0 and 1 will be modulated by using the data that is coming from the quantum random number generator, right? So this is called there is a chip, like a IC is there, that is called the QRNG chip. So that will generate the 0s and 1s. Then these 0s and 1s are fed to the FPGA. Then FPGA will process the data and modulate the actual laser to generate the qubits.
Okay.
So the randomness is coming from the QRNG chip, quantum random number generator. So this will generate the zeros and ones, then that will be used to modulate that laser to generate the quantum states or qubits. And qubits cannot be stored, by the way. Qubit cannot be stored.
Okay.
It is like modulating and then it is going to the channel. It cannot be stored.
Sir, from KV Razu, he asked that, good evening, sir. My question is to do BTech, MTech projects on QKD, any hardware requirements or software?
For QKD, there are softwares are there, like QKD simulators are there for different vendors. And hardware system, hardware system will be a bit costly, but that your institution need to procure that hardware setups. And then for projects, there are different projects, like you can have some hardware implementation, or you can do some modules that can be done in software. So both possibilities is there, both on hardware and software. But if you need to procure the hardware, that will be a bit costly. It cost around 80 lakhs or so.
Okay.
So, but if one institute can procure this type of setup, then it can be used, say multiple groups can visit there. They can take their data and they can have a hands-on experience. So it is not that a central facility can be created in a university campus and multiple colleges can access, like in a time scheduled manner.
Okay. Any other the questions? Okay.
And as you are all aware, the DST and AICT has launched a curriculum last year, and they are starting some quantum courses in the UG level and master's program also.
Yes, sir. Yes, sir. That's right. Okay. Any other questions?
Good evening, Arka ji. This is Mehboob Hussain.
Yes, sir. Yes, sir.
Sir, thank you so much for briefing quantum key distribution. Like what's the applications you are performing on CDOT. I have like one general query that if like the university like we are working under proposed laboratory and curriculum for communications part and quantum communication, like how CDOT may help the university or the individual institute to set up a laboratory for all the students who wants to work on quantum communication. And also, please brief that like maybe if it is an the application, how many users can maybe at a time they can work on.
Okay. So actually the CDOT, the model is that we generally what we have done in other case of say JIT or NSUT. So they have given us the order to deploy the QKD link there. So we have, after getting the order, we have deployed the link there. Our team, 2-3 persons went there, installed the system, and their faculty and student took a training. So the training can be say for 1 day or 2 days, and they took a training to how to operate the system, what different experiments they can perform. And after the link is up, then we provide remote support. So the system comes under say 1 year of warranty. And then we provide remote support. And in any case, if there is any issues that is not solvable remotely, then our team visits your place. That is always free of cost during the warranty period. And they makes the system any fault is there, they can repair that. The second thing is that we do not have any policy as of yet to give like theoretical training to any institute, right? So we cannot engage in that in the present setup. So we can only give that QKD setup to you and give an hands-on training to how to use it for different experiments. And as you are telling that how to use multiple persons, so this is a hardware-based systems, like, and this comes with one graphical user interface. So if your system is connected to a local area network, sorry. Yeah. So if you're
sorry, sir. Sorry. For simulation also we need hardware, sir.
No, we don't do any simulation because it is basically hardware-based solution. So it is actually generating the keys. So you can have the keys in a file and you can then analyze the keys. So I can share a list of experiment that is possible using our QKD solution. So I can share with Dr. Hussain also or Dr. Anil if you're interested. So you can see what are the experiments that are possible. Then you can take a decision. And as this is a hardware-based solution, you can form a group of say 5-6 people. So they can come together and they can take the data for sometimes say 1 hour or 2 hours. Then in the next batch, the other team can come and take the data. So in this way, the system can work. And this system work 24/7. There is no issue in that. So you can just have some form some groups and they can use it. But it is not something like remotely accessible by different persons at a time, because the thing is that then there will be conflict because the hardware is one. So if you say suppose one person is changing one parameter and other person is changing other parameter, so there will be conflict. So you can access it remotely, but at a one time one person or one group.
Yeah, got it, Arka. Yeah.
Yes.
Okay, sir.
Because this is a dedicated hardware, there is no simulation involved in it. It is a purely hardware-based solution. We have the lasers modulator inside. It will generate the keys. You can take the keys and develop your own application also.
Yes, yes. Actually, I wanted that, like, if the universities or institutions, if they want to develop this curriculum and want to really establish an QKD laboratory and want to work on real-time applications, I'm really wondering whether we need to establish the hardware and also work on the applications.
Sir, actually, if you see the syllabus, they do not mention that you need to procure QKD hardware, to be honest. Right, but the thing is that if you are giving something on theory, then I think it will be better if you have a like practical experience. So that will relate the theory with that live experience. So that's the thing. Yes. Otherwise, this syllabus, that curriculum, UG curriculum, at least they do not mention that you need to have a QKD system in your lab. But it will always be an added advantage if you have an actual system that is generating the QKD keys, and you are understanding all the steps that is there in the QKD system. Because if you see the curriculum, they have clearly mentioned the protocol names also there, BB84, COW, DPS. So these protocol names is already mentioned in the syllabus. So we support two protocols, COW and DPS. So based on your budget, you can go for any of these.
Yes.
And these systems later on can be used by your faculties or your PhD students, MTech students to publish some good papers and do high level of research. So it is not only the UG curriculum.
True, Arka.
Yes.
Okay, sir. Is there any other questions?
Yes, sir. Sir, I have one question, sir.
Okay, ma'am.
I am Dr. Arviya, sir, Aditya College of Engineering and Technology, sir.
Yeah.
I am working with QSkit library, sir. I generated key also for IBM developed, but when I started executing the application, part of the application I am able to execute, but for the remaining one, it is asking for some configuration init_py or some configuration file you have to do like that. I don't know, is there any software that we can execute our applications freely, sir?
Ma'am, actually, the thing is that what you are telling is related to quantum computing, that IBM QSkit applications, right?
Yes,
so I don't have much idea on that system actually, because I am working on communication part. And so I think that IBM, any support team from IBM can reply to your query better.
So where can we quantum compute? Hello, sir.
Yes.
Which software we have to use for practicing our applications, sir?
Ma'am, IBM QSkit is reputed one, but I don't have any experience in that.
Okay, sir. Okay.
Because I am working in quantum communication, and in IBM does not work in communication. So they are mainly focused on computing part.
So for communication, which one we need to practice, sir?
Ma'am, for communication, there is multiple QKD simulators from different organizations, and some of them are free, some of them are paid. But I can share you some links, but I can't I cannot promote any other organization. So I'll say, if you connect with me, I can share you some links.
Okay, sir. Thank you.
Okay, but CDOT do not have any simulators, so we have only the hardware-based systems.
Okay, sir. Thank you, sir.
Yes.
Thank you.
Okay, sir. Any other? Yes, sir. Thank you, sir. Thank you, Arka, sir.
Okay, thank you.
Thank you. So it is time for the vote of thanks.
Thanks to the JNTU team and Dr. Hussain also. I forgot to mention him. He connected with me to take this session. So I am grateful to JNTUGV for this opportunity, and Dr. Hussain. I met him during a visit to Kakinada.
Thank you, Arka.
Okay, thank you.
Okay, sir. It's
So-
time for vote of thanks.
Oh,
Sir. Okay, sir. Okay, sir. So good evening, everyone. As we come to the conclusion of today's insightful webinar organized by JNTUGV on the occasion of National Technology Day 2025, it is my privilege to deliver the vote of thanks. First and foremost, I express our heartfelt gratitude to Mr. Arka Mukherjee, sir, our esteemed resource person, for delivering an engaging and informative talk on Introduction to Quantum Communications. So your deep, insightful, and technical and the institutional aspects of quantum communications have significantly enriched our understanding, and we are confident the sessions will inspire further academic and research engagement in cutting-edge field. I will also extend our sincere thanks to Registrar Madam, Professor G. Jayasumma Garu, for inaugurating this session and offering her support and encouragement. A special thanks to our Vice Chancellor, Professor D. Rajalakshmi Madam, for her visionary remarks that underscore the importance of adopting emerging technologies like quantum communication in higher education. I also thank Dr. Mahmood Hussain for introducing us to Dr. Arka Mukherjee, sir. I also thank all faculty members, researchers, and participants from various institutions who joined us today and contributed to the success of this session with their presence and engagement. So let us carry forward the spirit of National Technology Day by continuing the explore, learn, and innovative in the service of science and society. Thank you all once again, and we look forward to your participation in future initiative. Stay safe and stay inspired. Thank you, sir. Thank you, sir. Mukherjee, sir.
thank you, thank you. So I am logging out.
Okay, sir. Thank you, sir.
Oh, okay, thank you, everyone.